We'll now discuss the sixth assignment. The first question, some circuit is given to you with two voltage sources and you're supposed to find the Thevenin equivalent between the terminals 1 and 1 prime. You know that the Thevenin voltage is the open circuit voltage that appears between these two. Okay. Now when you have two sources, you can use a variety of methods. I'll use superposition, that is you activate one source at a time and find the contribution to this voltage. So when I'm looking at the contribution of this 5 volt source, I have to set the other source to 0, the 10 volt source to 0. Then we'll have a single voltage source and some resistors. You have to find the division ratio. And this particular circuit, it's an R2R ladder where we have 2R branches this way and R branches that way. So it's quite easy. Looking this way, we have 8 kilo ohms because of two 16 kilo ohms in parallel. Here we have 16 kilo ohms. Here again we have 8 kilo ohms and 16. So all of this appears as a single 16 kilo ohm resistor. The contribution of this 5 volts is 5 volts times 16 divided by 32. So from this we get 2.5 volts. Now when you deactivate this source and do it from this particular source, the calculations are slightly more cumbersome but nothing fundamentally difficult. So you first have to find the equivalent resistance of all of this and substitute it between these two terminals, and then use successive voltage division to find the answer. Okay, I won't go through all the steps, but I'll just tell you that, for instance, looking this way we have 24 kilo ohms. Looking this way we'll have 24 parallel 16 kilo ohms, which works out to 9.6 kilo ohms. So looking this way we'll have 17.6 kilo ohms. Okay, so you can go on working that way and find that the contribution of this 10 volts to this voltage is minus 1.25 volts. Okay, so the Thevenin voltage, which is the superposition of these two, is 1.25 volts. Okay, so that's the answer to the first question. The second question, it asks for the Thevenin resistance, for which you deactivate all the sources, and from here you find that it is 8 kilo ohms, from here it is 16 kilo ohms, from here 8, from here 16, and from here again 8 kilo ohms. Okay, so the Thevenin resistance is 8 kilo ohms. So the answer to this is 8 kilo ohms. And third question, you have another network. Now it has a control source. You have to find the Thevenin voltage and the resistance. Thevenin voltage, of course, is the open circuit voltage between these two points. How do you find that? First of all, the current flowing this way is 60 microsiemens times Vx, and Vx itself, the voltage here is 2 volts minus 50 kilo ohms times the current. So Vx is 2 volts minus 50 kilo ohms times the current, which is 60 microsiemens times Vx, and this product is 3Vx. Okay, so if you solve for this, you will get Vx to be half a volt, and the voltage between these 2 points is 2 volts minus 200 kilo ohms times the current. Okay, so Vth is 2 volts minus 200 kilo ohms times the current, and the current is 60 microsiemens times half a volt. Okay, and this whole thing comes out to be 6 volts. So the Thevenin voltage is 2 volts minus 6 volts, which is minus 4 volts. Okay, If you look at the next question, what it really says is a positive resistance RL is connected between these two terminals, and you have to find the value of RL such that the power dissipated in RL is maximized. Now you know from maximum power transfer theorem that if you connect a resistance between these 2 points, the value of the positive resistance for which it will be maximized is equal to RTH. So basically you have to find RTH. That's all. Okay. How do you do that? You have to deactivate the source, but be careful to deactivate only the independent source. Okay. The dependent source and its dependence should be retained exactly as it was. And then you apply a test voltage or a current. So let me apply a test voltage V test. And if I do that, this voltage Vx is nothing but V test times the resistive divider ratio. So Vx will be V test divided by 4, and the total current here consists of the current there and the current over there. Okay. So the current here is nothing but V test divided by 200 kilo ohms, and the current here is Vx times 60 microsiemens. So Vx is V test by 4 times 60 microsiemens. This whole thing is the current that flows out of the driving source, and this is equal to V test 1 by 200 kilo ohms is 5 microsiemens. 60 microsiemens by 4 is 15 microsiemens. So the total is 20 microsiemens times V test, and V test by I test is 50 kilo ohms. Okay. So the resistance here is 50 kilo ohms. The resistance RL required is 50 kilo ohms. Next case, a similar question, but you are required to find the Norton current instead of the Thevenin voltage, and that you can find by short circuiting this and finding the current that flows in that direction. As with the first problem, we'll use superposition. First you deactivate this 8 volt source, okay, and find the contribution from this 5 volt source, and you can see that there is a short circuit between these two. Now between this and this, through this part of the circuit, there will be some resistance, but no current will flow through that because it is paralleled by a short circuit. And how much is the short circuit current? You can see that the voltage across this 10 kilo ohm resistor is 5 volts. So the current here is 5 volts by 10 kilo ohm, which is half a milliampere. Okay. So the contribution of this 5 volt source to the Norton current is half a milliampere, and similarly you can deactivate the 5 volt source and find the contribution from this. And in this case you have to do this parallel and series combinations of resistances and finally find the current through successive current division. Okay. And what is the current that flows that way? It will turn out to be 8 volt divided by 40 kilo ohms or 0.2 milliamps. So the total Norton current is 0.7 milliamperes. That is the answer. Okay. And here is another circuit for which you have to find the Norton current, and it includes this control source. Okay. So again you short circuit this and you have to find this current. Okay. That is the Norton current. Now you can see that the voltage here is 32 kilo ohms times Ix, and exactly the same voltage appears there and there, because once you short circuit it, this and this are in parallel. Okay. So the current here is 32 kilo ohms times Ix divided by 8 kilo ohms, so that is 4 Ix, and the current in this is 32 kilo ohms times Ix divided by 2 kilo ohms, that is 16 Ix. So this 5 milliamps, it divides as 4Ix and Ix. So 5 milliamps is 4Ix plus Ix, which is 5Ix, and Ix is 1 milliampere. Okay. So that we know. Now we have to find the current that is flowing there, and that is equal to Ix minus the current that flows this way. The current that flows that way is 16 Ix or 16 milliamps. So Ix minus 16 milliamps, Ix itself is 1 milliamp. So which flows this way, that is IN. IN is Ix minus 16 Ix, which will turn out to be minus 15 milliamps. Okay, so that's the answer. And in the next question, again you are asked what is the value of the positive resistance, which when connected to these 2 points will dissipate the maximum power, and that is equal to the Norton resistance Rn. Okay, so you have to deactivate the independent source here and find the resistance between 1 and 1 prime. So deactivating the current source, it gives you an open circuit. Then we have 8 kilo ohms, 2 kilo ohms. This is Ix, and the voltage drop is 32 kilo ohms times Ix. Okay, and you can apply either a test voltage or a test current, and in this case I'll apply a test current I test and find the voltage that appears between these 2 terminals. And this I test goes into this and it gets divided into these 2 parts. Okay, the same I test flows into these 2, and these 2 resistors are in parallel. So using current divider formula, you know that the current that flows through the 8 kilo ohm resistor is I test by 5. Current that flows through 2 kilo ohm resistor is 4 times I test by 5. Okay, and Ix equals minus I test by 5. So the voltage drop in this direction is 32 kilo ohms times minus I test by 5. 32 kilo ohms times minus I test by 5, and the voltage drop here is I test by 5 times 8 kilo ohms, and the voltage V test is nothing but the sum of this voltage and that voltage. Okay, so V test is I test by 5 times 8 kilo ohms plus 32 kilo ohms times I test by 5, or basically I test times 40 kilo ohms by 5, or 8 kilo ohms times I test. Okay, so the Norton resistance is 8 kilo ohms. The resistance you have to connect to absorb maximum power is also 8 kilo ohms. Okay, the next question, you are given some circuit with control sources. Okay, and you have to find the Y parameters. Now what you have to do is, first you short circuit this, apply V1. The current that flows there is Y11 times V1. The current that flows there will be Y21 times V1. Okay, and after that you short port 1, apply V2 to port 2. The current that flows here will be Y22 V2. The current that flows there in that direction will be Y12 V2. Okay, so that's all you have to do, and it's routine circuit analysis. I'm not going to sit and do the steps of the circuit analysis. I'm assuming that if you apply a single voltage source here, you will be able to calculate the current there and there by writing down appropriate circuit equations. You can use nodal analysis or mesh analysis if you want, but it can be done even without it because there is a single source. Okay, now if you evaluate it, you will find that basically y11 will be 0, y12 will be 0, y21 will be minus 4 millisiemens and y22 will be 8 millisiemens. Okay, and you can see that, let's say you have V1 applied here, then first of all you see that Vx itself equals V1. Okay, and Vy will be 0 in this case because port 2 is short circuited, Vy is across port 2, so it will be 0. So this will become an open circuit and this also will become an open circuit. Okay, and what do we have? We have this network 1/6 of a kilo ohm. Okay, and if you calculate the current over there, what happens is that you will see that that is exactly equal to 4 millisiemens times V1, and 4 millisiemens times V1 is being pushed that way. So the actual current flowing out of this voltage source, this is 0. Okay, so that's what you will see. Here you will see 2 millisiemens times V1 and this pushes another 2 millisiemens times V1. So the total current flowing in this direction will be minus 4 millisiemens times V1. Okay, so Y21 is minus 4. Similarly, you can calculate Y12 and Y22 as well. Okay. Again, another circuit, and you are asked to find the Y parameters. Okay. So the principle is exactly the same. Let's say you connect V1, short circuit V2, okay, and you have to find basically the current here and the current there. Okay, this will be Y21 V1 and this will be Y11 V1. Okay, so if you solve for this network, V1 this is short circuited and you're told that this is 2Ix where this is Ix and this is 2Ix in this direction. Okay, first of all, the network is symmetric completely, right? So it looks the same way from port 1 and port 2. So you expect that Y11 equals Y22 and Y21 equals Y12. And when you apply V1 like this, what happens? This is 400 ohms, this is 400 ohms, and this is also 400 ohms. Okay. Now it turns out that the current that flows that way in the resistor, this will be 2 times V1 divided by 1200 ohms. Okay, so that's what the current is going to be, and the current here is half of that, which is V1 divided by 1200 ohms. Okay, and this Ix will be minus V1 divided by 1200 ohms because of its direction. Okay, and what do we have here? This is 2 times Ix. Okay, so which really means a current that is flowing that way, which is equal to 2 times V1 by 1200 ohms. So you can see that the actual current drawn from the voltage source, that is 0, right? Because 2 times V1 by 1200 ohms is flowing this way and 2 times V1 by 1200 ohms is flowing that way. So this will be 0. And this 2Ix again, it is 2 times V1 by 1200 ohms in that direction. Okay, so the current flowing here will be the sum of this one and that one. Okay, the current flowing there is V1 by 1200 ohms. This is 2 times V1 by 1200 ohms. So this is 3 times V1 by 1200 ohms. Okay, and this is the negative of I2. So Y21 V1 will be minus 3 by 1200 ohms times V1, or minus 2.5 millisiemens times V1. So we have Y11 which is 0 and Y21 which is minus 2.5 millisiemens, and by symmetry we also know that Y22 is 0 and Y12 is minus 2.5 millisiemens. Okay, if you're not sure of the symmetry, you just calculate those things as well. Okay, so that brings us to the end of the 6th assignment.